this lecture is going to be on the basics of what is a force. A force is simply a push or a pull, and this push or a pull leads to a change in an object's motion. Now we can look at this and we can start talking about balanced forces, and we're going to call something a scenario or a phenomenon that has balanced forces. We're going to call that equilibrium. So the rocks over here are stacked and they are stationary. The rocks are considered to be in equilibrium since all the forces acting on the rocks are balanced. So there are two forces acting on these rocks. There's gravity acting downwards, and there's a normal force or a support force acting upwards. So force diagrams are representations of the forces acting on the objects. So what would a force diagram look like of you sitting in your chair right now? Draw it. Well, the pause is just to make sure you realize that you have a downward force, F of G, and you have an upward force of the normal force, or the support force from the chair. So your diagram would look much like this right here in this picture, in this force diagram, which is very much like this scenario here. Net forces. Net forces involve the total magnitude, right? The amount and the direction of all the forces acting. Most often, more than one force acts upon an object. The combination of all forces acting on an object is called net force. Net forces lead to changes in object's motion. And forces can act in any and all directions. And in class, we looked at what we call forces acting in the x direction, which is horizontal, and forces acting in the y direction, which are vertical. So let's look at this scenario here. An applied force. Here, if I have two forces acting on this object here, and it doesn't matter what the object is. I've got a 5 Newton force and a 10 Newton force. That object doesn't differentiate, or it simply feels a 15 Newton net force acting upon it. So if they're acting in the same direction, they would add together. Notice this scenario here. I've got 5 Newtons acting to the left and 10 Newtons acting to the right, where they cancel one another out, or in this case, they subtract from one another. And there's a net force, right? Net of 5 Newtons acting to the right. Right? 10 Newtons is 5 Newtons greater than 5 Newtons to the left. So therefore the net force is 5 Newtons to the right. And notice here in my third scenario, I've got 5 Newtons acting to the left, 5 Newtons acting to the right. They cancel one another out, and we would say that 0 Newtons is the net force acting on this scenario 3. The net force depends on the magnitudes, right? How much? And the directions of the applied forces. But there are many types of forces. Right? When we talk about types of forces, we're still talking about the different types of pushes and pulls. That we have forces that are in contact with one another. We call them, we could say friction, where frictional forces, as we will study in class, F sub F. Force of tension, F sub T. Normal force or support force, F of N. Air resistance, we'd call that F sub AR. Applied force would be F sub A. And spring force, which we won't do much with, but force sub S, or spring. And then we have other forces that act over distances, gravity, electricity, and electrical and magnetic. But these different forces we're going to start applying to the same concept. So let's look at what this diagram here is showing, because diagrams show what is going on. So let's say this individual here is holding a rock. When the girl holds the rock with as much force upward as gravity pulls downward, the net force on the rock is 0. This rock is stationary, and it has no net force acting on it. The forces canceled one another out. Just like they did in this scenario acting horizontally, in this scenario they're acting vertically, and they cancel one another out. So therefore what we can say about this is this rock is not accelerating. It is not speeding up, it is not slowing down, and it is not changing direction. Another force that we'll look at is the force of tension. And tension is a force that is applied or found within strings, rope, and or chains. That we can look at this. If we're weighing something, so this bag of sugar, right, here's the scenario from this guy in the picture, that it weighs 2 pounds, that the weight of this sugar, right, F of G downward is 2 pounds, or 9 Newtons, those are both weights, that the tension in the string is 2 Newtons upward, that the force of tension in this is 2 pounds, or 9 Newtons upward, and downward its weight, or F of G, is 2 pounds. Or 9 Newtons, both of which are two different ways to measure the same thing. So mechanical equilibrium, and you should have been able to read about this in your textbook. If the forces are balanced, then the object is not accelerating. This is key. This is a very, very important part here. It is not accelerating. If the forces are balanced, it is not accelerating. If the object is accelerating, whether it is speeding up, slowing down, or changing direction. These are 3 different ways an object can be accelerating. Then we can say that a net force must be present, right? If something is falling towards the earth and accelerating, we're going to say, yeah, there's a force acting on it, and that force is gravity. But if an object is moving, yet there's no force acting on it, it is not accelerating. So mechanical equilibrium. So here's a scenario where this painter is walking from this side to this side. Or I don't know, maybe they're window washers, I don't exactly know. But the sum of the upward vectors equals the sum of the downward vectors and the scaffold in the equilibrium. So therefore the total downs add together to equal the total ups. And we would say that this scenario is in equilibrium. So here's another force, the support force, or what we'll call F of n, the normal force. That we're simply saying that whatever force is acting downward, there must be an opposite force or a counter force acting upward in this case, presuming they are in equilibrium. So here's an example where I have F of g downward and normal force F of n upward. Here I have the applied force downward, it's my hand applying a force, and the spring force, or F of s, acting upward. And here's my weight, or F of g downward, and this is my support force, or F of n, acting upward. Remember, I prefer force diagrams to be drawn like this, and not so much like this. And moving on to the whirlybird. So let's apply this. So our new application to air resistance is that air resistance is going to be an upward force. That the whirlybirds that we create allow us to engineer paper to control the amount of air resistance acting on the paper. We control the design, so therefore we control its performance, or how it functions as it falls toward the earth. While falling, gravity is acting downward, and air resistance is acting upward. Both of these forces are acting on the whirlybird. So we're going to be getting some practice drawing some force diagrams. So I'm going to have you, if you're to this point right here, and you're looking at this slide with me right now on the screencast, here's what I need you to do. I want you to pause it, and I want you to draw a force diagram for 1 through 6. And it might challenge you a little bit, but you'll get the hang of it. If a book is at rest on a table, diagram the forces that are acting on the book. Remember, F of g is an easy one to be thinking about downward, and the normal force is your support force. So that'll get you started. Notice number 2, a girl, she weighs 90 pounds, is suspended motionless from the ceiling by 2 ropes. We're going to be looking at tension. Tension is the force. But notice, there are 2 ropes. So you're going to draw the diagram. Number 3, an egg is free falling. Remember, if an object is in free fall, only gravity, or F of g, is acting upon it. Be careful when you are drawing the diagram. Notice it says neglect. That means ignore, or consider air resistance to be 0. When we say free fall, we're saying only gravity is acting on the object. Number 4, a flying squirrel is gliding from a tree to the ground at a constant velocity. Consider air resistance. Consider means air resistance is in your equation. Number 5, a rightward force is applied to a book in order to move it across a desk. Consider frictional forces. Neglect air resistance. So now we're going to be looking at both y direction forces. These should be balanced, but you'll find that x direction forces will not be balanced. And last but not least, a rightward force is applied to a book in order to move it across the desk at a constant velocity. Consider frictional forces, neglect air resistance. So you're drawing diagrams. Draw your diagrams from 1 through 6, and then you can test it on the answer key, which I'll be posting now. So be sure to pause it. Here goes. Here's your answer key. Number 1, a book at rest on the table. I've got an F of g downward. I've got F of n upward. Number 2, a girl suspended by the 2 ropes. F of g is downward. The F of tension, well, each of the ropes would have 45 pounds of tension acting within inside them, because 45 plus 45 is a total upward of 90, which is equal to her weight downward. Number 3, the egg in free fall. Anytime it's in free fall, you only have F of g acting downward. Number 4, the flying squirrel is at terminal velocity, and this is a term we're going to get into in this unit. Terminal velocity tells me that it's moving, but the net force acting on it is 0. That F of g downward is equal to the F of air, or F of air resistance acting upward, that these are balanced. It is moving, but these are balanced. And we call this terminal velocity. Number 5, a book sliding horizontally on a desk. Remember, my y components, my vertical forces are balanced. I have F of g balanced with F of n upwards. But my applied force is to the right. My applied force is greater than the force of friction. So there is a net force, so I am accelerating this book to the right, or in the direction of the net force. Notice my applied force is greater than my frictional force. So it must be accelerating in this direction. And number 6, it says the book is sliding horizontally with balanced forces. So notice this is in equilibrium. My normal force, my F of n upward, is equal to F of g, so it's balanced in my y direction. But notice my applied force to the right is equal in magnitude opposite in direction to my force of friction. So what I can say about number 6 and number 4 is that objects can be moving, but they cannot be accelerating. Objects can be moving with no net force acting upon them, as long as they are not accelerating. And according to number 4, we call terminal velocity a way in which an object can be moving and not accelerating. And number 6 here, we can see that a book can be moving and have your y forces and your x forces balanced.